Hi, can you hear me? Great. Hi, I'm Tim, and today I'm going to be talking about my project assessing heat adaptation strategies during future heat waves through dynamical downscaling. And before I start, I'd like to thank my supervisor and collaborators on this project. So, as everyone in this room has heard over and over again, cities are facing increasingly more intense and more frequent heat waves. So, I believe that we should be quantifying urban environmental outcomes during these heat waves, both contemporary and projected future heat waves. To that end, that's what our project is about. We're going to be examining multiple climate-related outcomes in these heat waves, including heat stress in the form of UTCI, space cooling, and urban ventilation outcomes. And we're going to be examining that in cities with contrasting climates, the hot, arid city of Phoenix in the southwestern United States, and Toronto, Ontario, which has a much more humid continental climate. We're going to be accounting for projected urbanization and climate change in our simulations, and we are going to perhaps explore how cities can adapt to any potential changes. To pursue that goal, we are using an entirely physically based framework. So the core of our modeling framework is the Ruhr-University regional climate model. Using that model, we're going to downscale G, GCM data and reanalysis data. And we're going to further downscale that, the output from MORPH, into a microscale radiation model, tough pedestrian, which can calculate incident radiation and TMRT on pedestrian at different locations within the urban canyon. So using the TMRT output from that and combining that with the air temperature, humidity, and wind speed from WRF-BEM, we'll be able to calculate pedestrian heat exposure in the form of the UTCI at different locations through the urban canyon for different climate scenarios and for different urban configurations. We're also going to be examining building energy use and tracer concentrations, which we can derive from WRF-BEM itself. So here's some few more details about the methodology. We simulated 1 year return period heat waves for the start of the century and for two different climate scenarios at the end of the century using WRF 4.3.3. For Toronto, the boundary conditions were provided through satellite data in the form of, which we processed, using the WRF and LCZ generator suites. For Phoenix, we used ICLUS urban land use, land cover, and population and density data. And the neat thing about ICLUS is that there's different projections for different time periods and different RCP scenarios. So, for example, here's the impervious fraction data, and we see that we have different urban fractions for start of century, end of century RCP 4.5, and end of century RCP 8.5. And finally, a note about any our tracer emissions is that we emitted only at ground level, and we assumed that it was impervious to, it was proportional to impervious fraction. So we'll start by examining space cooling energy use. What you're looking at is space cooling energy use over a diurnal cycle during a 1 year return period heat wave. And the dotted lines represent end of century urbanization, population, urban development, and while the solid lines indicate start of century urban development. the colored lines are end of century climate change, while the black lines are start of century climate change. And we find that for Phoenix, the difference between the dotted lines and the solid lines is much greater than the difference between the colored line and the solid line, which indicates that, well, for Phoenix, we expect that the increase in urban development and urban density and population is expected to have much greater effect on space cooling energy use than is climate change. For Toronto, we didn't have the same projected urbanization data, so we could only limit our analysis to climate change and its effects. However, we found that even only considering climate change, we expect air conditioning energy use to double under an RCP 8.5 scenario. Looking at, turning our attention to pedestrian heat stress, we find that for Toronto especially, we're expecting a very substantial increase in strong heat stress for all of the 3 locations, and for both RCP 4.5, but especially for RCP 8.5 scenarios. For Phoenix, the increase is not quite as, so for Phoenix, we're looking now at hours of extreme heat stress, and we're providing that the increase is not quite as substantial, but it is still present. With our methodology, we're able to, we were able to attribute the increase in UTCI to its different variables, and we find that air temperature we expect air temperature as expected to be the primary driver of the increase in UTCI. However, we find that mean radiant temperature and humidity changes are also appreciable and should not be ignored. So now we now know that, well, we expect heat stress to increase, and the question turns to, well, can we adapt to that increased heat stress? So Kranoff and others have found that while we can adapt to air temperature only under RCP 4.5 scenarios and only under an extensive implementation of adaptation strategies. However, for RCP 8.5 scenarios and at nighttime, we really couldn't. However, I'm not aware that he's investigated shading or humidity-based adaptation strategies. So that's what we did in this study. We looked at the effects of cool roofs, green roofs, reflective pavements, and PV roofs, as well as street trees on pedestrian thermal stress and their associated effects on space cooling energy use and tracer concentration. For street trees, we used a fully coupled Whorf-Bet tree model, including two-way coupling. So let's start with space cooling energy use. We found that for space cooling energy use for Toronto, cool roofs were the most effective mitigation strategy, and for RCP 4.5, it was effective at reducing space cooling energy use down to contemporary levels. Of course, this is only considering the effects of climate change, and we're not considering urban development here. We also note that PV roofs can, while they don't perform impressively here, they can generate electricity to offset the increase in space cooling energy use. For Phoenix, now that we're considering increases in urban extent and density, we find that really there's not really a good adaptation strategy that will let us adapt all the way to contemporary cases, bring it down to contemporary cases. In terms of pedestrian heat stress, we find that trees, in this case, are the most effective heat adaptation strategy, and that they're almost able for Toronto under an RCP 4.5 scenario to bring it down to base level. And they're the most effective adaptation strategy we examined, mainly due to the shade that they provide pedestrians. Finally, we're going to look at the effects of the adaptation strategies on pollution dispersion. And what we find in general is that the most effective strategies in terms of space cooling energy use and outdoor thermal comfort are also projected to increase the pollution concentration. They're most expected to increase the tracer concentration, and that's because the cooling effects that they provide and their associated decrease in the mixing and planetary boundary layer height. So in conclusion, we see that increases in UTCI from climate change are mainly due to the increases in air temperature. We found that building energy use was driven primarily due to urban extent and density changes. We found that street trees can be effective in reducing pedestrian heat stress and that cool roofs can be effective for space cooling. However, we found that maybe we shouldn't write off climate mitigation just yet because these adaptation strategies really couldn't fully adapt to projected climate change, especially under RCP 8.5. I'd like to acknowledge our funders and also Amir and Alberto for their help in modeling. Thank you.
Thank you, Timothy. Any